popped up our innovative idea. Which is, why can't we just predict the seizures before they even happen and save the patients from all the suffering? Although there are some existing solutions, those solutions are only concerned with detection, meaning that the patient would still have to go through this dramatic, heartbreaking event every single time. In addition, the patient would have to undergo a complex, expensive surgery to have the device implanted. Needless to say, the dilemma of undergoing the same expensive surgery every 2 to 3 years to only change the device's battery. All in all, not only do the existing products cost a fortune, but also not as practical and accurate as our product. During a seizure cycle, stage transitions take place. The main stages are pre-ictal, which is the period of time before the seizure onset. Then comes the ictal, which is the interval during which the seizure occurs. After that comes post-ictal, which is the period immediately succeeding the end of a seizure. And finally the interictal, which is the time between 2 consecutive seizures. Since our main focus is seizure prediction, so our classification problem was between the pre-ictal period and the non-pre-ictal period, including interictal, ictal, and post-ictal periods. These stage transitions are conveyed by EEG signals. Electroencephalography, also known as EEG, is a monitoring method used to record electrical brain activity. Thus, one can forecast upcoming seizures by inspecting changes in EEG recordings. Our product comes in 2 versions. A wearable head cap with our FPGA chip embedded in, or an FPGA chip implanted inside the patient's brain. And this will depend on the user's preference. Data and algorithms are the most important basis of any machine learning project. This is why choosing the dataset was one of the most critical concerns. After plenty of researches, CHBM IT data was found to be very promising and our best match. The first phase in developing our project was the software phase, in which we had to train and test our system using the EEG recordings obtained from MIT using the SVM machine learning algorithm. SVM was the most suitable classifier for our classification problem. In order for the SVM to accurately classify between the pre-seizure class and other classes, certain features had to be extracted to ease the classification process. We settled on 4 linear features and 1 non-linear feature, which we believed yielded the highest results. When it came to results, performance metrics were needed, which are sensitivity, specificity, and accuracy. Here came to our minds an exotic idea, which is data segmentation. We believed it would boost the performance results since more detailed characteristics and properties of the data will be captured. And in fact, they did. next phase was the hardware phase, in which we had to map all our codes into an HDL code so that it can be burned on our FPGA. The hardware phase steps were as follows.